basically ready?
Yep. I think I got
All right.
Okay.
So without any further ado, I don't know how many of you guys have done research on OSX. LLDB and GDB suck balls. So hopefully we will learn about a new debugger that will make OSX research much less painful. So without any further ado, please give a warm welcome to Tyler and Brandon.
Sweet. Thank you, guys. Thank you. Don't get your hopes too high. The debugger is still in alpha phase. We had to rush a bit, so it's not super great yet, but I hope you can get some news, get some stuff out of the concepts.
Well, there's some great content. You just gotta have a great time.
It's a great Apple security talk, not just for the debugger.
So yeah, I'm Brandon Edwards. This is Tyler Bohan. Who we are? We're security researchers for BAE Systems. We do exploitation prevention, detection, and creation. Our job involves a lot of reverse engineering and bug hunting. And previously, we'd been mostly on Windows, but we started diving into OSX, and that's sort of what this talk is about. So to give you guys a little bit of background about how this all began, we had this fuzzer, and it's a funny story because we spent like a few weeks, months, years crying and writing a fuzzer, and it's really like language aware and smart and fancy and does all this cool shit. And just on verifying the output from the fuzzer, we're like, is the fuzzer even like generating stuff? So like we run it and it like generates like a handful of files, and then we like just open them, and like on file like 1, it does this to Safari. And so we're like, oh, sweet. Like, how lucky. Like, we just stumbled into, like, Safari bugs. And then, well, yeah. So we quickly find this crash. And we're like, maybe we should use, we should figure this out. Like what is this crash? Here's this crash. It's like, we're pretty good at Windows. We're pretty good at Linux. We're familiar with GDB. We love WinDebug. We've written debuggers for both, because ptrace is awesome, and the Windows Debug API is, like, unparalleled. Feature-rich, really helpful, awesome, well-documented, correct in documentation, everything that Apple is not. So we were like, man, we can just debug this. So we pop open LLDB, and we're like, okay, now what? And we're like, man, this is a novel debugger, though. It's pretty cool. It's how nice of Apple to include this really cool novel debugger. Not only is it a novel debugger, but it's actually a debugging novel. So to get anything done in LLDB, you have to write, like, like legalese, basically. It's sort of like inefficient and unusable. It's feature rich and awesome, and has like a bunch of cool stuff that our debugger like does not at all, and I'm not at all. But for the record, LLDB is awesome. It's super feature rich, really well tested for what it does. It just doesn't do what we needed, and we'll get more into what that means. But to give you guys an example, if any of you are, how many of you are familiar with GDB? Right. And I don't know how many of you are familiar with LLDB, but I don't want to depress myself by seeing other people hurt, so I'm not going to ask for a raise of hands. But if you see the GDB command, we all know, like, / some size WX memory address. How do you achieve that in LLDB? You start with dear LLDB, comma, and then you write this small essay in order to get access to it. And like, that's just viewing memory, right? Like, what if you wanted to actually do something? So the other thing we wanted is scriptability. And LLDB does run scripts, but it's an environment that loads scripts, not something you can script from outside of that environment. And so we wanted something where we could write scripts for complex debugging scenarios, like crazy memory tracking. You're like, I want to put in my Van M. DeBouse tree to do heap correlation to figure out when something's free if there are references anywhere else by having this complex range tree, blah, 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 blah. And you're not going to write that in LLDB scripts and then load in a script. And we'll show you why here in a minute. But when you're debugging, well, at least when I'm debugging VR shit, you're like, I got a bug, I want to write an exploit. I like to write a lot of scripts to reproduce the conditions, analyze things around them, whatever else. So that's why we wanted this. It has this Python scriptability available, but it's mostly meant to be used inside of it, and it's not the same as what we'd normally want. So let's show you what we mean by that. Like, you see LLDB here. You've got this import LLDB, this function. This is a sample taken from a blog, by the way, and what you can see is like it's like a text fortress to set a single breakpoint. This is a single breakpoint, right? Like, why is it 10 lines? Anyway. So you can see that like we have a single breakpoint where we have strings to refer to a function as our callback in the same piece of code. that we refer to down. Basically, like, this is not how programming should be for writing anything scriptable. And like these words, it's just like so verbose. Target.breakpoint create by name and then in quotes like the function you want. It's just so many words. Like look how many words you have to type. It's like you get the joy of writing Java with the speed and type safety of Python. It's just so many words. Like how would you get, like what if you actually had to get something done? How would you get any of those words into like a single line? You'd have to be Busta Rhymes. So like, and by the way, look at this. What is this? Look at this. Handle command. So we've written this file. We want to load the file. And then the file, which already was self-referential, if you remember from like 15 lines up in this thing, you have to then run a command that runs a command. Because, yo, dog, I heard you like writing commands in your debugger scripter commands. So, like, your script has to call back to the debugger to run the command that tells the script about the test. Like, does toast? I don't know. But, like, all right, so anyway. Scriptability. The one thing about this is that there's no way you can just script its functionality from outside of it. You can run LLDB and you can call scripts with that awesome syntax, but you can't just be like, yo dog, I want to write a cool script. And here's what inspired us. Here's what we were used to. We were pampered because of like Visigoth and like VDB type things where here's vtrace to write a breakpoint, where most of this slide is actually me describing vtrace, where the other slide was a wall of text. A text fortress of LLDB. And as you can see here, just like import the thing, write a callback, breakpoint equals callback, add the breakpoint. We just want simple, concise functionality. And so like this is one that you would run inside of VDB. Here's one that you would write that's like standalone. And like that's really where we were trying to go. And by the way, by we, I mean Tyler. I had this idea and I was like, I really want to write this. And so I'm like 30 now and dead from hacking. So like any good manager, I was like, you should write this. And Tyler wrote all the cool shit that's in this talk. I just want to throw that out there. I'm here as his fanboy mostly. And with that being said.
All right. So the first thing about any good research project is you research what else there is. And this bit slicer is probably the best debugger outside of LLDB that you can find. It's very similar to WinDebug in the fact that it is very easily used in a GUI, has great watch points. It's really integrated well with Objective-C, but it's a game cheat engine. That's what it's used for. But with that, you can read memory, you can write memory, you can set breakpoints. Where it lacks is actually in the debugging part. It does work with Python. It has a Python framework, but it's very, very limited. And you can tell it's for games. It's designed for games. But if you just want to search memory in your program, this is a great tool to use. So BitSlicer was really something that our debugger also took a lot from. Like I took a lot of ideas and methodologies that BitSlicer uses and put them into our debugger. Then you have debuggers such as Ragweed. Ragweed's probably 5 or 6 years old, and it was written for PowerPC or 32-bit Intel OSX versions. It uses a bunch of ptrace commands that simply don't exist anymore. It uses old versions of the mock commands that I'll talk to you about later, and it simply just it's not nearly ready for 64-bit processes. And as most of you should know, Mac is only 64-bit now, so that basically makes Ragweed useless.
It's also written in Ruby.
Yeah, and who uses Ruby anymore? Ruby security is a whole thing. Nobody writes Ruby. And he already talked about VDB, but as you see, Windows, Linux, FreeBSD, OSX, kind of. It can like read memory, write memory from OSX, but it has no sense of exception servers. It has no sense of breakpoints in OSX. It's really lacking. So that led us to trying to write a C backend that could maybe even be supported by VDB at some point. It didn't quite work out that way, but that was the idea. So next is how do we get there? And these two books are great. The one on the left is written in 2006. It was written for PowerPC as well, but despite it being written for PowerPC, it actually turned out to be almost more useful than the more modern version written for 64-bit OSX. They're both great books, and this is pretty much between these two books you can do what we did. So this just shows us an example of what we had to work with. Like I said, we've both written debuggers in Windows before. We've written debuggers in Linux, and they're all really well documented. If you Google OSX debugger, you get nothing. You Google LLDB scripting, you get nothing. Nothing comes up with this. And OSX, so the first place I looked was OSX ptrace. Right? Ptrace must work, because if ptrace doesn't work, how does GDB work? How does LLDB work? Well, and we'll get more into that in a second. Just for reference, all this following slides are all the backend in C. We'll get more to our Python implementation later on in the talk. I just want to give you guys a little bit of background on the mock APIs and things so you could have a better understanding of how the debugger actually works on the backend. Because at its core, this is just a debugging framework. We wrote Python bindings and things on top of it, but if you want to write in Node.js, you want to write in Ruby, you want to write whatever you want, this should be easily accessible to any language. That was kind of one of the big ideas. It's a very easy plug and play. So how do we do it? So I started with ptrace. Ptrace only allows attaching and detaching, and it doesn't even allow attaching and detaching. If you do ptrace attach, that's going to pause your program, and you're never able to continue again. You have to use the ptrace attach continue flag, and that's the only way LLDB attaches with ptrace. There's no peak memory, there's no poke memory. So basically, at this point, I just threw away ptrace.
There's also like no follow fork. There's like a lot of things that they've like. It's like Apple took like oh, BSD is awesome. Let's take all the cool shit out of it and then add like bonjour and that's like right. So ptrace does not work.
Ptrace is totally useless, but what you'll find is every single debugger for OSX uses it, and I didn't know why, so I just threw it away and I didn't use ptrace at all. And so then when I started my research, I come here, uninformed. Notice on the right it says June 2006. So that's a 10-year-old blog post, but this is actually one of the most helpful blog posts I could find. And even though it's so old, there's just so little information on OSX debugging and these sorts of things. So this talk is kind of just trying to show everybody how demystify it, if you will, make it less scary. So then the next couple slides are just showing how you do the same things ptrace does. So ptrace attach, you attach with this task for PID, and it gives you a port number. And that port number is used in all the mock APIs from here on out. So anything you want to do with mock APIs, read memory, write memory, set breakpoints, all that kind of stuff, you need this port number for. So this is your attaching. But what's interesting about attaching here that's different from ptrace is attaching is non-invasive to the process. So the process doesn't know that you have attached to it. It's not really attaching in that sort of...
It doesn't change any of the behavior of the process, much like if you're on Windows and you attach and it starts, there are like things like is debugger attached, like the heap goes into a special mode, like right, it starts using debugging functionality, all those other things. This is so far detached from that, no pun intended, that like yeah.
Right, we bypass all those checks. So if you have any sort of debugger checks, like iTunes, for instance, has a is debugger present check at the beginning, that has no knowledge of what we're doing. It would have no way of knowing that we attach to it. So it's just an interesting idea that happened to come about the way we designed this. So this is just the mock APIs for reading and writing memory. This takes care of ptrace, poke test, poke data, poke user, all those little fun little ptrace things are taken over by these funny mock APIs. You'll also notice that a lot of code that you find on GitHub and stuff uses just VM write and VM read instead of mock, but mock is guaranteed to work for 64-bit, so that's why we went with mock.
Yeah, after 32, you have to use these.
So this is reviewing and setting register state, pretty straightforward. This give us more of the ptrace functionality. Then the big change comes in exception handling. Because with ptrace, what you can do is you can just ptrace to a process and then just call wait. You can just wait for an event to happen, a signal to come. That's just not how it works here. Here we have to register an exception handler with the kernel, and when the kernel gets a message, it'll pass it up to the exception server. So this will sit in a loop infinitely, waiting, and when it gets a message, it passes it off to catch mouse exception raised. Notice the things that gets passed to it. There's no real way of knowing what breakpoint hit or what happened, what caused this exception to happen. So what we had to do was have to keep a lot of internal state to keep track of what actually caused these breakpoints, what caused the exceptions to happen, and so that caused a little bit of overhead for the exceptions. So the other thing that ptrace does is it catches all your signals. So signals tell you that a process forked. Signals tell you that a process exited. Signals tell you anything that a signal can happen. So what can we do? That's where we introduce this idea called KQs. KQs is another thing that's left over from BSD. I don't even think Apple really meant to keep it in there. It's just a legacy piece of code that somehow happens to be there. But what KQs give us is the ability to track exits, track forks, track execs, track signals. It also gives you a million other things, like reading file descriptors, reading from sockets, all sorts of stuff. This just happened to be the ones that we used for our debugger.
One note, though, is that those don't stop. It's not as though like you receive a message and it's waiting for your response. KQ is just a notification. Right.
It's up to us to decide what we want to do with that. So we allow you can register exception handlers, and that will then choose what to do with those calls. So this is just a general example of what it looks like. So k-event is the message. When k-event gets something, it'll drop down, and it ends with these bits to see what actually happened, and then it'll do stuff based off of those. Notice that we have note child and note tracker. Well, those aren't available on OSX. They got rid of those. Those are things that will allow you to follow the fork. So if we fork, note tracker is going to tell us, hey, the child's PID is this. Oh, great, we can follow fork. But you can't follow fork on LLDB, you can't follow fork on GDB, and I was wondering why. And this is definitely at least one reason why those things happen. They neutered this call, which makes it impossible for us to follow forks. So we had to try to find some workarounds and get that working in a different way. So just that's it for like OSX internals. Just a more recent protection that's come up, just that's interesting for debugging, is system integrity protection. It was introduced in September in El Capitan, and essentially it just blocks where you can write, and it blocks what programs you can attach to. So every Apple program you can't attach to anymore. You can't, with LLDB.
Yeah, it's like based on certain like flags on the programs. If it's an Apple signed binary, if it's in a certain path, you can't attach to it.
So, and then you also can't write to, there's various areas you can't write to. Protect locations are bin, system, user, SBin. You can't write to them at all. And LLDB cannot attach to any of those programs at all. It's very easy to disable this, but for attackers and such, it blocks lateral movement and makes it much more difficult to traverse these programs.
Right. So like you find a bug in like whatever Apple app and these things. You want to debug that to write your exploit. It's pain.
As you'll see in a couple slides later, we've run into this protection numerous times. It's actually become a huge pain in the ass to deal with this stupid protection. So I've been turning it off and on multiple times. Yeah, this is a little example showing it blocking it. And then we have our little debugger. It's nothing fancy, but we have a little thing that we can, if you exec a program, you attach to a program, then exec over it, it will map Safari or whatever into that address space, and you're still attached to it. This, unfortunately, LLDB, bit slicer, all those things, they break on exec, and they don't work on exec anymore. So if you try to do the same protection, you hit exec, LLDB is like, hey, I'm done, I can't do anything. But because our program doesn't really care, it follows the exec, loads the Safari into it, and we can bypass SIP and use our debugger on any program we want with very simple commands. It's super easy to do, and it works really well. So that basically wraps up for the OSX internals. Just to reiterate what we want, we want something that's easy to use, friendly interface, and we want something lightweight. LLDB is very, very, very heavy, and we want something that's easily scripted. So how do we get that? We have to write our own. This kind of sucks. Usually you can go out, find a tool that works, and use it, and not waste so much time writing your own stuff. But at the same time, it's actually really cool to learn about a lot about the OSX internals and spend a lot of time understanding how OSX works and how it differs from BSD, from Linux, from some of the other platforms. So again, to reiterate, our goal was never to replace LLDB. We're not going to be able to replace LLDB. LLDB has a ridiculous amount of functionality. It would take years, and they spent years writing such a great debugger. The problem with that, though, is you have to read a novel to understand how to use it. The LLDB scripting, while yes, it's very verbose, it's not easy. Easy is not a word I would use. And we wanted to offer a lightweight interface. We did not want to offer this. So, and that continues on far further than I could ever put slides on. There's 2,268 Python functions available in LLDB. That would take you weeks just to read and understand all these LLDB functions. And also, if you Google LLDB scripting, there's like 4 examples. If you go on LLDB's website, there's one example, and it doesn't even really do anything. It just sets a breakpoint and it searches a red-black tree to find a node. And that's all it does, and that's the only Python scripting example at all. And then they link you this reference. What am I supposed to do? Read this reference? I spent like 2 or 3 weeks reading the reference and trying to understand this before we decided to go our own way. So yeah, LLDB is very, very, very heavy. So one more time, at this fun LLDB script, just take a quick peek at it, and then this is the introduction to what our debugger looks like. It's very similar to VDB, not exactly like VDB, but very similar, about 5 lines of code, and should be pretty straightforward what it's doing. All right, so some of the interesting ideas. We are the only debugger that I know of that's using KQ rather than ptrace. Like I said, it has some downfalls with it, but it also has a lot of upsides. The fact that we're non-invasive to process means we can attach and detach from processes multiple times without anything ever happening to that process. So I can attach to a process, read its memory, try to find strings, do different things to it, and it never knows I was there. We also have a concept of lazy exception server registering. So when you register an exception server, the program then knows you're there. That is invasive to the program. You're registering an exception server, so any exception that happens is now going to your exception server. What we do is we don't register that exception server until we're absolutely necessary. So if all you want to do is read process memory, or you just want to peek around inside a process, you're never going to register an exception server. That way, the program never knows you're there. You don't have to worry about running out of exception ports. You don't have to worry about any of that sort of stuff, and it allows us to debug lots and lots of processes at once. Another interesting idea we have is lateral movement code injection. We wrote a couple functions that, as you see, to inject code that allocates into memory and writes that code as readable, executable in that memory. We also have create threads, so you could easily backdoor some programs. You could easily inject yourself into another program, spawn off a thread, and have that program running have your program running inside another program very, very easily. Unfortunately, our SIP bypass thing will not work on that case, so...
Rumors have it, though, there are other ways to get around SIP.
Right, SIP, yeah. We haven't had a ton of time to dive into SIP, but we got around it relatively quickly. I'm sure it's not too bad to get around. Programs. So it's just a stupid, simple example showing I can attach to 10 processes at once and just put them in a list, and then I have 10 processes debugging. And there's really no way you can do that in LLDB without having 10 different terminal windows opening, attaching to all different 10 terminal windows, and commands parentheses over and over and over, trying to get your way around. So I'm glad you like it. I have a demo for you. So like I said, we wrote Python bindings just because I like Python, he likes Python, lots of people like Python, I'm sure most of you like Python, but with the rise of languages like Node.js, that's totally possible to take these and take the exports and just wrap them in Node.js and wrap them in whatever language you're choosing. We didn't want to make anything very specific to Python. All our Python is really just wrappers around this framework. It's nothing special. It shouldn't take, if you look at the code, it shouldn't take you more than a couple days to write Ruby wrappers, Node.js wrappers, any wrappers you want. It's just, all this does is export functions. It's very easy to extend.
Mind if I do the recap?
Go for it. One more thing. It's also easy to use in C. So I don't know about most of you guys, but I actually prefer writing in C than Python. So you can, I wrote a couple examples just to show you that it's all very, very easy to use in C. If you don't want to use the overhead of Python because it's a lot slower, you can easily do all this in C.
So there's this little recap because there's this funny set of events. Like the talk started out as like, here's a debugger, here's how we wrote it and why we wrote it. But along the way, we stumbled into like way more ODay than we ever wanted. Well, that's not true, but then we expected. So we start with this like Safari crash, right? We're like, lol, awesome Safari ODay. We need a cool debugger. And Tyler's like writing the debugger, and he's like, man, I keep panicking the kernel with these debugger APIs. So now we're going to demo this like kernel like OSX, like kernel ODay based on this. It's actually two of them, one of which is not as reliable as the other. So we've got like one really consistent one, and then we'll demo. But we stumbled into two, or he stumbled into two. What's great about that, though, is while writing the slides and finding jokes and putting Buster Rhymes in our slides, we kill Keynote. So we've got some Keynote bugs as well, reproducible. And then we dragged Keynote into IDA, and guess what happened? So if you... just throwing all that out there. There's a little recap of our process of events, and now the hilarity of the talk begins with you guys get to see a bunch of Apple bugs.
Just a heads up, the Safari bug has been patched in the latest version of Safari. They just patched it, so I can demo it for you on a VM with an old version of Safari, but it has been patched, unfortunately.
Yeah, but the Keynote and 2 OSX and bugs are legit.
Two kernel bugs, the IDA crash. You guys can actually reproduce IDA crash on your own. Just buy Keynote, put it in IDA, and then you're done. That's all you have to do. So I'll do it for you if you want, but you don't have to. It's pretty straightforward. As a prank?
Yeah. Oh yeah.
Yeah.
All IDA bugs are pranks, bro.
Right.
Like this.
Right. So, then I'm just gonna go into a couple demos, just showing you guys the basics of the code, and then I have a couple slightly more verbose demos. But I'm gonna see if I can mirror my screen. So give me like 2 seconds. I swear I know how to use computers. There's a way to mirror this, isn't there? Oh, mirror. Just because it's easier, because I can't see anything. Is that somewhat readable, or do you need to make it bigger? You're welcome. All right, so let's get this. Let's go here. All right, we're just going to look at the basics example. Is that big enough or bigger? Bigger, or are you good? Good? Okay. All right, so this basically how it works is you just add these breakpoints like this. You can add breakpoints by address, You can add breakpoints by offset. You can add breakpoints by name.
Oh, yeah, so symbol stuff.
Oh, I see Jordan over there.
And the author's right next to him, Rusty.
Oh, Rusty.
So, yeah.
So, Rusty, we're currently using your parser. We're writing our own parser. It's just not done yet.
But we haven't included yours with ours. We just give people a link to your stuff.
Right. So unfortunately...
So for symbol parsing, you should download Rusty's code until we publish our terrible code.
Right. We're going to put it on GitHub later this afternoon, and we're going to put a link to your stuff. But because your parser was awesome, but we're writing our own. It's just with all these bugs and stuff, we've run into so many problems just trying to get the stupid thing set up. I spent the past week dealing with these crappy bugs and kernel crashes and all these things, just trying to get it going.
Do you know how tempting it is to spend more time debugging a Keynote Ode rather than writing about your Keynote Ode in Keynote? Like, right. It's...
So yes, all the symbol parsing stuff is from Rusty. It's super awesome. But yeah, you can breakpoints by name, breakpoints by offset. And you just make these little callbacks, and your callback functions can really do anything. This one just does a pretty print thing I made for the talk, so it looks nice. And all you'd really do is you just do debug.attach or debug.run, and that's it. So I'll just show you how it looks. Oops, I know how to type.
Everything has to be run as root, by the way. That's one thing I think we may have skipped over. You have to be root to be debugging anything. Yeah. All
right, so basically just a couple breakpoints to hit, and this is just a stupid little pretty print thing that prints out some registers for you, and then it prints a little bit of assembly. It depends on Capstone. If you don't have Capstone, it's fine. It just won't print that out. And then we just throw a little stack trace at the bottom. Pink is text segment, blue is data segment, green is just a disassembly, and it's just showing you the different breakpoints you hit. If you notice that we hit breakpoint D90, this is a function, and the function arguments are 1, 2, 3. And it's supposed to print out 1, 2, 3, but just for demo's sake, we print out 99, 2, 3, just to show that we can set thread state, get thread state, all that sort of stuff, just showing the basics. Then we'll show some reading and writing memory stuff. You like the crash message? Yeah. It's a good one. I thought it was a good one. All right, so reading and writing memory, we just allocate a page, we write AA to it, we inject hello. I then just dump those locations to prove that it's actually working. And then, just for fun, I search through them to make sure that I'm actually getting the same things here, just to make sure our search things work. We search for blue, because blue is in the binary, but it also shows up more than once. And then, just hex dump some stuff, but if you notice, this one is the same one that we injected earlier, just to prove that everything is working as we say it's working. All right, back to Keynote first. Yeah, back to Keynote for a second. All right, so searching memory. Let's say I can search multiple programs' memory at once. It's not like the most useful thing in the world, but you can. It is helpful to be able to see, like, if you have multiple instances of VLC running, something happens to one. Which one am I looking at? It's very easy to programmatically do this, whereas with LLDB, this would be very difficult to do. So, bear with me for a second. So we just spawn up VLC, make sure I have my sound. Spawn up VLC with a couple different songs. Beat 2, and then beat 3. And then we search through the memory using, and then so I just want to look for beat 2 just for fun's sake. Actually, we'll look for beat 1. And then you just type in what you're looking for here, beat 1 to beat 3. And this is just going to search the program memory and try to find which programs have this. That's bad. That's not good. Sudo? Oh, I did sudo, didn't I? Yeah. Base add, yeah, it's not attaching to that process. Oh, sorry, you have to do this. pgrep VLC and pipe it in PID. My bad. We can do it, and then it searches through the programs. And hopefully it comes up with some solutions. Sometimes this one doesn't work, but there you go. So we can tell the first program has all these in it. The other programs come up with some solutions as well because they also have memory from the first VLC that spawned up.
From fork and whatever.
So you notice you have all those. But if you look for beat 3, it should only come up in the last one. And it's also searching the whole program's address space, so that's kind of why it's a little slow. Okay, so you can see that the programs are forked off the first program, so they inherit the memory from the first one, so that's why it came up in all of them. But when you look for just the last one, it just comes up in the last program. And then the next one is dummy binaries. So dummy binaries is great for malware. It's great for packing binaries. It's also cool for Apple because Apple thinks they're very cool and they like to encrypt their binaries. They have this, what they call Apple protected binaries. They encrypt things. They mostly encrypt it for proprietary information. They don't want you to be able to run Apple software on other hardware. So they encrypt it. They encrypt some of their very key programs to make sure that you can't reverse them and set up your hardware to work on your hardware to work with their software. But the problem with encryption is they have to decrypt it at runtime. And if we bypass SIP, all these programs will be under SIP because they're all Apple programs. All Apple programs are SIP protected from the beginning. So if we bypass SIP, we can easily dump out the memory, and we can then potentially static reverse it. We could do whatever we want with it at that point. So to demo that, I am going to just run strings on the binary. And a string I thought that probably should be inside of Finder is Apple, right? The string Apple I can imagine would probably be in there because it must be because most of their function calls have the word name Apple in them. So we'll just grep -i, so it doesn't even matter case, and we'll just grep Apple just to prove to you that's an encrypted binary. We run it, you get nothing. And to actually see if it's an encrypted binary, you probably don't care, but I'll show you anyway. System, library, core services, Finder, core, Finder, O2-L, and then you go to load command 1, and load command 1 has, at the bottom of load command 1, it has something called flags. If your binary is encrypted, that flags will be 8. If your binary is not encrypted, it'll be 0. So that just shows you that the binary is indeed encrypted. So now I will do a little SIP bypass to show you that we can bypass SIP, and we'll dump the binary out, run strings on it again, and you'll see that it all works well. So you just do .sip run, and you put the program you want to run. It sits there and waits for you. You go over here, sudo Python dump bin sip.py, and you put in that number 7423. Go back, spawn the process, come back over here, hit enter. It dumps it, and it dumps in something called decrypt.bin. So if you run the strings on decrypt.bin, and then we search for Apple, again, -i, just because we can. You'll notice it comes back with all these results. So, and so, just for conversation's sake, you can even open something up like this. I guess I'll use Hopper just for fun, but you can use. You can open this up, and then you can actually see the. Are you guys laughing at my demo? Don't worry, my demo version of IDA. I mean, Hopper. I have a real version of IDA, I promise. And then somewhere in here, source, Python, decrypt.bin. It's still going to say it's encrypted because that flag is still set to 8, so it still says encrypted. But if you notice, if you look at the bin encrypted style, it doesn't have any of this stuff. It doesn't have entry points. It doesn't have anything. Now you have actual code, and you could actually do something with this. You could reverse it. You could do whatever you want with it to figure out whatever you're trying to work with. It's just an easy, simple way to bypass Apple's encrypted binaries, and kind of shows that their protections aren't necessarily the most verbose things in the world. So back to Keynote for a minute. I think I got one more good one. All right, ASLR. So it is 2016, and if everybody remembers, probably 2008, 2009, Dino and a few other people posted stuff about binaries on Windows that didn't have ASLR. You could just drop to these binaries without ASLR, and you were money. So I figured that would just be a funny little thing to test on OSX just to see. When I say ASLR, just to clarify, I mean the position independent executable part, loading the text segment at the base address every time. I don't mean ASLR on libraries. I don't mean ASLR in a stack or heap. I mean pi, where the base address of the program is the same every time. So I was just curious as to what programs are doing this. So let's kill off some stuff. So how I went about doing this was I wanted to watch a movie, so I turned on Firefox, because I like Firefox to watch my movies with. So then I went and I just closed. I went and watched my movie, and I found that Firefox is loaded the same base address every time, no ASLR. So I was like, okay, let's see what else I can find. So then I wanted to download a torrent. I use Transmission. That's my personal favorite torrent client. So I do it again, and notice here, Transmission shows up. Okay, fine. I won't download any videos off Transmission. I'll watch one from my computer. So I open up VLC, because VLC lets you change the aspect ratio, which QuickTime doesn't, so everybody uses VLC. I do it again, and notice that, oh wait, VLC also doesn't have this. Okay, so I'm going to stream from Popcorn Time. You know that illegal Russian torrent streaming site? I'm going to search from there. Okay, so I run it again. Oh wait, and this one, there's Popcorn Time. So now I'm going to watch, you know what, fuck this, I'm going to watch something on Windows. You know, Windows is the way I'm going to go, so I'm going to turn on my Windows VM, watch a movie there. I come back, I do it again, and notice, VMware. So all these, these are just the programs I had on my computer just to have. Like, these are just the ones I have. Like, I'm sure most of you guys have different programs than I do. So these are just the ones I personally had. And all I can really say is that all Apple programs opt into Pi. But a large amount of binaries that are not from Apple opt out of Pi, which I feel like is a huge security problem and a huge thing people should be aware of. I was definitely not aware of this until a couple days ago when I wrote this. I think most of you probably aren't aware of it as well, and it's very interesting. Back to Keynote. All right, ASLR. All right, what do you want?
Also under development or whatever.
Yeah, I'll show them the code base at the end.
All right. Yeah.
All right, so the key here is I would say this is somewhere between alpha and beta. It needs one fresh rewrite, because I probably have 8 search memory functions right now, when I could have just one. The problem is with all these crashes and things I've had with the kernel, all the problems I've been having, I haven't had time to just go through and give one whole clean rewrite. So please, I really hope you guys all check it out and look at it. And within the next month, I would imagine there's going to be a whole new naming system and a whole new thing. So if you start writing scripts for it, a month from now, it's probably not going to work. We need a few things to add: watch points, testing, a bit more functionality. Like I said, there's some rush code for the test. I wrote like a search string function that literally I wrote yesterday just for this, just so you guys could see, because my search memory wasn't quite cutting it. And then stop crashing the kernel, Keynote, Safari, just got to stop doing that because that's not working out too well for me. Yeah, so I just listed a lot of people, and because I felt like there was no real area I could go and find all the information I need to find about OSX and about setting up a debugger, writing your own debugger. If you go through and you look at these 20, give or take, blogs, you should easily be able to write your own debugger, set up your own things, and it's not too bad. These slides are more really just to try to put all of the OSX debugging-based stuff into one area. Credits. And then these are some of the people on our team that helped work on the program with me. Yeah, and so don't ask questions yet. We're not done. But the code will be released on my GitHub. I'll probably release it a little bit later. I just have to remove Rusty's code before I push. And then I'll be ready for push, and I'm going to make a to-do list. I'll make a README on it so that you guys can know how to put Rusty's code back in to make it work. But that's that. And then
O-Day time.
All right. So just an FYI for Hopper. Let's just see here. I know, I only have the demo. It's not good. I don't even remember where I put it, honestly. It's called like Hopper Crash somewhere. I don't know where it is. There it is. All right, so then we found this while also trying to reverse things. So that happens. And so if you look at the report, you can see it is a bad access SIGZAG-V. This happened while simply trying to debug some of the programs so we could figure out what the hell we're doing. So this is a big setback for us. And then we were like, oh, let's write some stuff for Keynote, and I'm going to write these cool pictures. I'm going to put these fun things in there. And so I put all this fun stuff in Keynote. Oh, wait. Shit, there goes Keynote. And then I got one more thing for you, but I want to show you the code base real 2 seconds. I want to spend 2 seconds showing you. Oh, I don't have internet here, do I? I don't have internet here, but okay, so I guess I won't show the I won't show you the code base that way. I'll show it to you this way. It's pretty straightforward. The source file is all the C files. I have C examples in here, and Python has all the examples, and all the Python bindings and stuff are wrapped in libs. So all the examples here, they all import from libs, and libs is where all the stuff lives. So anybody that's here, this parse file will be deleted. To get this program running, go to Binary Ninja GitHub, take his Mako parser and put it here, and it'll work.
If you guys want a BSD license, just do a solid. That'd be great. Yeah.
Licensing issues were a problem. That's okay though. And then, so it's 4:40. We're a little early, but that's okay. Unfortunately, I'm not releasing this to you guys because I haven't had a chance to debug it myself yet. So I don't want to release full kernel ODay without at least testing it first and seeing if it's worth any money, because I don't want to give you guys free money. But so then we have this file called kernelcrash.py, and we run that, and we type in our password, and goodbye. Any questions, comments, concerns?
Oh, you can't see his screen. His screen's way funnier. It's a bunch of spaghetti. It's like.
Don't worry, it'll restart in a minute.
It'll be on. Yeah.
I never done it actually with it connected to something else, so I didn't know what it was.
I don't think the kernel's able to think about the thing right
it's
now.
It's like I don't know what the hell's going on.
It's a little.
So there's that, and if you just play around with the debugger and stuff, you might be able to stumble upon
you'll stumble into bugs just trying to do stuff.
I literally was setting up a different computer for backup today, and it crashed probably 4 times just setting it up. So there's definitely OSX kernel problems, and there's OSX security problems in general. So that's kind of one of the takeaways on the talk. Like the debugger is great and everything, but the state of OSX security is a little lacking. But they do work, except not really. I'm still not doing anything. I don't know why. It's just stuck. I actually think I might have broke it. Does anybody have any questions, comments, concerns? Sure.
You said that there were some disadvantages to using the K key rather than the H trace. So what exactly were some of the disadvantages?
You don't get the ability to halt, notify, and then resume type of thing. The KQ just tells you that something happened.
Right.
So ptrace is like you hold up to a signal handler and you're like, I choose what to do, and then it continues. This is just something happened. It just tells you.
And then so it's up to the user to. So we have a theory of registering. This exception, you can register exception servers, and you register exception callbacks. And your exception callback can then do stuff with that message, but by default, it just is saying, hey, there's a fork happened. So what we've been working on writing and stuff is a fork happens, okay, let's break on that fork, and let's follow that fork. So that was a big thing that we tried to do. And unfortunately, we kind of ran out of time, but...
right, we've got code that we inject into fork, into the PLT. It pushes a new return address and spins the child process, and then we can attach. So no new opcodes execute in the child process until you attach and then nop that out. But and you can do that in LLDB if you're a masochist and want to fap out like 400 lines of code. But it was one of the things that we implemented, but it will not be released yet until it's a little more refined.
Right. So I'm gonna try to push the code this afternoon, but the internet here, as you guys know, is kind of shitty, so it might not get out till tomorrow. But if you just check out github.com/blankwall, I guess I can pull Keynote back up and leave that slide up.
Did your box come back?
Yeah, it just restarts. So I'll link it on my Twitter. I'll tweet to him if you guys want to follow us, but it will be at this link. It's just private right now. And I guess if you guys give me permission, I'll just post it. It's fine. I thought it was a GNU license, and we were under the impression. Okay.
Oh, we love you. All right, we'll just release the whole thing. Thank you, guys. Can we get a round of applause for these the Binary Ninja guys for right now just relicensing their shit to help us out?
That's awesome. We greatly appreciate that.
You guys kick ass.
Right. What time is it? I don't know what time it is, but we have like 5 minutes. So if you guys have any other questions or anything, feel free to answer them, or we'll talk. Or you guys come up. Yeah. What's up?
Well, he flashed us 10. Yeah.
Yeah, we will get around SIP. We just didn't have.
Oh wait, to repeat the question. Sorry, the guy held sign. He said we casually throw out SIP bypasses, and are we looking more into ways we can work around SIP? And the one that we showed was just using exec where, like, it was like the ASLR bypass in Linux like 10 years ago. You exec something, and then you inherit the process space, blah, 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 standard system call. Everyone knows how it works. So that lets you bypass the fact that, like, you're now attached to a binary that just inherits the other binary. There are other things you can do while running, but we are looking into that. I don't know if we'll publish anything. Why are you? Well, we'll chat. Let's chat at the bar. I'll buy you some shots. We're gonna get some secrets.
All right. Sounds good.
We did look at dtrace. Did we look at dtrace for debugging, Tyler?
We looked at dtrace extensively. We have a 1,000-page book on dtrace. Dtrace. The problem with dtrace is it's more of an observing tool. You can observe and you can get a lot of analytics from it, and it's in the works to actually run it from our debugger, so you can run it and get the analytics
Run
and get
dtrace scripts,
and get the output. So you hit a breakpoint, run a dtrace script, get those things, and dtrace works amazing. But it's just there's no real introspection. It's only analysis. You get information, but we were looking more for introspection and being able to actually
Like inject code and do shit like that.
Right. But dtrace is amazing. It's a wonderful tool. We probably should have put a slide about it.
Yeah.
Now that I think about it.
Any other questions? Awesome. Thank you all. Oh, wait, sir.
All right. Breakpoints. So you register an exception server, and then wherever you want to write the breakpoint, you write a CC byte there. And when that CC byte gets hit, we have an interface structure that holds all our breakpoints. So that CC byte gets hit, and from the CC byte, we can see what address that hit. And from that address, we can look through our internal structure and match it up to the breakpoint address.
Well, so like, and that, I think the thing that he sort of lightly went over earlier is that, like, you start out non-invasive, like right off the bat, where, like, we're just observing things, we can read memory, whatever. When you add a breakpoint, on the back end, the debugger registers that exception handler for the exception server for you. So until you do something like add a breakpoint or whatever, the program has no way of knowing you're attached. When you do that, though, the lazy binding, as you call it, like we register the exception server, and the exception server then catches when the sig trap happens, and whatever the in3 or in3 happens, and so and then we just look up the data and correlate right back to bytes, single step, blah blah blah, whatever. Standard breakpoint behavior after that. It's cool though, because what was that? Following the execs, I mean, I don't know why they're so terrible at it in other debuggers. We didn't actually have to change anything.
It's not really following. You just
we just stay attached.
Yeah,
It's just LLDB doesn't do that.
Right.
Yeah, LLDB doesn't do that. Yeah, it's really weird. Yeah, so his question is like, did we have to do anything special for the exec? It's like, no, it just casually works out to be a really convenient bypass.
When LLDB or GDB hits an exec, they bail. They say, I can't handle that. What we do is we just let the exec map over our process space.
Just keep going.
Just don't worry about it. Say again?
Fork. So yes, we do this. We basically we set a breakpoint at the PLT. We inject a new return address because fork doesn't actually take we set another return address because fork doesn't take arguments. You can do whatever with the stack you want. So when and that return address goes to a code cave that spins. When the child process forks, it just sits there, returns to the spins. You attach to it. No new code executes in the child process. You then knock out that code cave, and then it goes down to return. Return goes to the original address, and you're out.
All right. That's it. We'll be around for the rest of the evening. Want to talk about anything? Please come up.